We will now discuss about the elimination of arbitrary constants in a given equation through differentiation. We all know that differentiation will always result to a differential equation. However, when there is an arbitrary constant in the given equation, after differentiation, it may happen that the arbitrary constant will still persist in the resulting equation. Hence, it will be a challenge to work on the given equation and the resulting derivatives to come up with a differential or a differential equation which is free from an arbitrary constant. Supposing that we are given the equation y equal to ax squared plus ax plus 4, where a is an arbitrary constant. We proceed by differentiating both sides with respect to x, and we get y prime equal to ax plus a. So it is now a challenge for us to come up with a differential equation that is free of the constant a in this example. In the following examples that we will work on, we will differentiate in as many times as there are arbitrary constants in the equation, and then we shall strive to get a final answer free of any arbitrary constant. Let us now work on the following examples. Y is equal to ax, where a is the arbitrary constant. So we differentiate with respect to x. We write y prime or dy dx equal to a. Y prime is equal to a is a differential equation, but notice the presence of a in the equation. So we will get a corresponding equation that is free of the arbitrary constant a. What we do is we simply substitute y prime to a in the original equation. So we'll be getting y equal to y prime x, or y equal to xy prime, or xy prime minus y equal to 0. Another way of writing this is by using dy dx instead of y prime. So we cross multiply, we will be getting y dx equal to x dy, or y dx minus x dy equal to 0. Next, we have y equal to ax plus b. What we have here are two arbitrary constants a and b. So what we will do is we will differentiate twice. First derivative y prime is equal to the derivative of ax, which is a, plus the derivative of b, which is 0. So applying differentiation process again, the derivative of y prime is y double prime, and the derivative of the constant a is 0. So we have a second order differential equation, y double prime equal to 0, or we can write it in the form d squared y over dx squared equal to 0. For our third example, we are given y equal to e raised to x plus a. What we do first is we rewrite this as y equal to e raised to x times e raised to a. e raised to x plus a is the same as the product of the exponentials e to the x and e to the a. Now, let b be equal to e to the a because that is our constant. So our equation now will become y equal to b e to the x. And there is one arbitrary constant. No? One arbitrary constant. So differentiating once, we get y prime equal to b e to the x. But we know that b e to the x is the same as y. So y prime is equal to y. Or dy equal to y dx, or y dx minus dy equal to 0. We now go to the next one. Y is equal to sine of x plus a. There is one arbitrary constant a, so we are only allowed to differentiate once. So y prime is cosine of x plus a. So we pause for a while and ponder on this differential equation y prime equal to cosine of x plus a. Notice the persistence of the arbitrary constant a. So what can we do to these two equations so that in the end our differential equation will be free of the constant a? Let us square both sides of these two equations. Square both sides of 1 and 2. Okay? So we'll be getting y squared equal to sine squared of x plus a. Let us call it as 1.1. And then same thing for the second equation. Y prime squared is equal to cosine squared of x plus a. That is 2.1. Okay, so at this point you probably know what will happen or what will be the next step. We're going to add equations 1.1 and 2.1. So adding corresponding sides, we get y squared plus y prime squared equal to sine squared of x plus a plus cosine squared x plus a. And we know that this is a trigonometric identity equal to 1. Hence, our equation is y squared plus y prime squared equal to 1. Another way of writing the equation is y prime squared equal to 1 minus y squared. First order equation, degree 2. First order differential equation of degree 2. Next, we go to equation 5. Y is equal to a e to the x plus b. We have two arbitrary constants, a and b. So we differentiate twice. y prime is equal to a derivative of e to the x is e to the x plus the derivative of b is 0. Differentiating again both sides of the equation, we get y double prime equal to a e to the x. And clearly, the differential equation is y double prime equal to y prime because a e to the x is equal to y prime, or y double prime minus y prime equal to 0. Next, y equal to a sine of x plus b. So here we have again two constants a and b. We differentiate twice. Y prime is equal to a. Derivative of sine is cosine of x plus b. And then y double prime is negative a sine of x plus b. But a sine of x plus b, a sine x plus b is equal to y. So y double prime is equal to negative y, or y double prime plus y equal to 0. For number 7, we have y equal to a sine of omega t plus b. Omega is a parameter and it is not to be eliminated. No? The parameter not to be eliminated. It's only a and b that we have to get rid of. No? So again, there are two. So y prime is equal to a. Derivative of sine is cosine omega t plus b. But by chain rule, what is the derivative of omega t plus b? That is omega. Alright? So y double prime is a omega, is a constant. Derivative of cosine is negative sine of omega t plus b. Again, by chain rule, the derivative of omega t plus b is omega, so it becomes omega squared. Alright? And we see that a sine omega t plus b is exactly equal to y. So we write this as y double prime equal to negative omega squared. A sine omega t plus b is our y. So y double prime plus omega squared y is equal to 0. Okay. Next, y is equal to ax squared plus bx plus c. There are three constants, so we differentiate 3 times. No? Differentiate 3 times. Y prime is 2ax plus b plus the derivative of c0. So that is the first derivative. Second derivative, y double prime is 2a plus derivative of b0. Finally, our third derivative is y triple prime equal to 0. Next, y is equal to c sub 1 plus c sub 2 e raised to 4x. There are two constants, c1 and c2, that we need to eliminate. So y prime is equal to derivative of c1, a constant is 0, and then c2 remains as c2. Derivative of e to the 4x is e raised to 4x times 4. We are allowed to differentiate twice, so y double prime will be 4c2, and then the derivative again of e to the 4x is e to the 4x times 4. That is equivalent to 16 c2 e to the 4x. 16 is 4 times 4 c2 e to the 4x. And what do we see here? 4c2 e to the 4x is equivalent to y prime. So y double prime is equal to 4, and 4c2 e to the 4x is y prime. So y double prime minus 4y prime is equal to 0. Next, let us try y equal to c1 e to the minus x plus c2e raised to, say, x over 2. Constants to be eliminated, c1 and c2. Y prime, derivative of c1 e to the minus x is c1 e to the minus x, and the derivative of negative x is negative 1. Plus c2 e to the x over 2, the derivative is c2e raised to x over 2 times the derivative of x over 2 is 1/2. Okay? Then we proceed to y double prime. Negative c1 e to the minus x is negative c1 e to the minus x. Again, the derivative of negative x is negative 1, so it becomes positive. Plus 1/2 c2 e to the x over 2. The derivative of x over 2 is again 1/2. So this becomes 1/4. That becomes 1/4. Alright. So let us multiply everything by 2. 2y prime, negatives 2, c1 e to the minus x plus c2 e to the x over 2. Okay, just to get rid of the fraction. So for the second one, it becomes 4y double prime equal to 4c1 e to the minus x plus c2 e to the x over 2. Alright? What do we do next? We can now, what is the best thing that we can do here, huh? Okay, so we have here 3 equations, 1, 2, and 3. Alright? Yes. What we do is we eliminate C2. So equation 2 minus equation 1. And what do we get? 2y prime minus y. Okay? You see that? 2y prime minus y. Then negative 2c1 e to the minus x, and this one, negative 2c1 e to the minus x minus c1 e to the minus x. What do we get? That will be negative 3 negative 3 c1 e to the minus x. And then c2 e to the x over 2 minus c2 e raised to x over 2 will give us 0. Okay? So let me call this as equation 4. Next, equation 3 minus equation 1. That the purpose is again to eliminate C2. So 4y double prime minus y, 4y double prime minus y is equal to 4c1 e to the minus x minus c1 e to the minus x. That gives us 3c1 e to the minus x. And c2 e raised to x over 2 minus c2 raised to, or c2e raised to x minus 2 will vanish. Alright, so what do we have here? We have equation 5. So what do we do now? With equations 4 and 5, we simply add 4 and 5. So 4y double prime minus y plus 2y prime minus y equal to 3 c1 e to the minus x minus 3c1 e to the minus x. That will be equal to 0. So we have 4y double prime plus 2y prime minus 2y equal to 0, or 2y double prime plus y prime minus y equal to 0. There. Okay. What number are we? 11. So we have, let us say, y equal to c1 e to the ax cosine dx plus c2 e to the ax sine of bx. C1 and C2, A and B are parameters. Hence, they are not to be eliminated. Two constants C1 and C2, we differentiate twice. So y prime equal to C1 e to the ax cosine bx. It is a product. So start with the derivative of e to the ax, which is a e to the ax cosine bx. Okay, and then plus c1 e to the ax. Derivative of cosine is negative sine. So let us change that to negative sine bx, and then the derivative of bx with respect to x is b. Okay, then plus, we go to the next one, c2. Derivative of e to the ax is a e to the ax sine bx plus c2 e to the ax. Derivative now of sine is cosine of bx, and the derivative of bx is b. Alright, so two terms at the right side. After differentiation, it will yield 4 terms at the right side. So if we proceed to y double prime, we will be generating 8 terms. But there is a way of abbreviating our computations. What do we see here? We see this expression, c1 e to the ax cosine bx and c2 e to the ax sine bx, which is exactly our y, right? So These two will be replaced by ay. So we write it as y prime equal to ay minus, let me factor b in the two remaining terms. b c1 e to the ax sine bx. Factoring negative b here, it becomes negative c2 e to the ax cosine of bx. Alright? Then we proceed. Y double prime, derivative of ay is ay prime minus b. Here we have c1, derivative of e to the ax is a e to the ax sine bx, plus c1 e to the ax, derivative of sine bx is cosine bx times b. Then minus c2, derivative of e to the ax is a e to the ax cosine bx, minus c2 e to the ax, derivative of cosine bx is negative sine bx times b. There. So, what do we have now? What do we have now? bc1 e to the ax sine bx. Do you see this? bc1 e to the ax sine bx, and then c2 e to the ax cosine bx. There. You see that? Common to them is a. Alright? So, we shall replace it by y prime minus ay. Do you see that? This expression, let me encircle this. This expression, okay, including the negative sign, is equal to this together with this, right? There. You just multiply it by a. Alright? So we shall write it now as y double prime equal to a y prime plus a times y prime minus ay. Okay? This entire thing, negative b times the quantity, is equal to y prime minus ay. Alright, and then what do we have here? We can factor, from the two remaining terms, we can factor the b. Let me use another color there. We can factor the b here, right? Together with the b in front. So that will be negative b squared. And c1 e to the ax cosine bx, c2 e to the ax sine bx is equivalent to y. Right? That is equivalent to y. So what do we have now? Y squared equal to ay prime plus ay prime minus a squared y minus b squared y. Y double prime equal to 2ay prime minus a squared plus b squared y. Okay? Or y double prime minus 2ay prime plus a squared plus b squared y equal to 0. Okay?